In this video, we'll be using a combination of geometric thinking and algebraic thinking to derive the spherical mirror equation, which looks like this. It says that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Let's see how we get there. So first we note that at this object location O, we have a tree, and rays are going to spread out in every direction from this tree because it's a diffuse reflector. So we want to pick special directions for the rays that we care about, and I want to look at just a few rays. So one way we can often approach problems is by considering symmetry of the system. So I know that each little bit of this curved mirror behaves like it's a flat mirror that's locally tangent to the circle here. What does tangent mean? It means perpendicular to the radius of the circle at each point. So exploiting symmetry, we can say that one ray comes from the top of the tree here and hits the very center of the mirror along that principal axis. I know that this makes some angle. I'll give it a name. I'll call it theta. And if it comes in at angle theta, we know the angle of incidence equals the angle of reflection. For a plane mirror, it behaves the same way here locally on the spherical mirror. So we have two rays here. They converge at a point, and these two angles are equal. Remember, if we have many rays that leave a point on the object, and they're all brought together in some other location in the same pattern they had when they left the object, that's where we find an image. We can add another ray here coming from the same point on the object. We can bring another ray from the same point on the tree through this special point, the center of curvature of the circle. And I know that if this came through the center, then this line segment here is a radius of the circle. And what that means is if the light came in this way, it will reflect back along the same line. So we already have enough rays here to see where the image will be. I have two rays that left this point on the tree, and they converge on this point here. So we know that the image is going to be located right here. Now we can name some distances on this diagram. I know that this is the location of the image. So from the center of the mirror to the location of that image, I'm going to call it d sub I. That subscript stands for the image. I will just pronounce it di. Similarly, we have this distance from the object to the mirror. We'll call that distance do. A well-labeled diagram is half the battle here when we're trying to explain relationships between quantities. And a third distance that I know about is the radius of curvature of the mirror, which is measured from the center to the location of the mirror. So this is r right here. Now we know that corresponding parts of similar triangles are similar, so we want to look for similar triangles in this system. Do you see any? Well, I know that right triangles are similar to each other if they share one other angle, since the sum of the three angles is 180 degrees. So we can just look for some right triangles that share an angle. Let's see. How about this triangle right here that includes the image tree and that angle theta? Here's our right angle right here. Do you see a triangle that's similar to that triangle? This one right here. So we know these two triangles in the yellow are similar to each other. One thing we know about similar triangles is that corresponding parts of similar triangles are proportional to each other. This is the object, this tall tree here. So let's say that its height is the height of the object, ho. And of course the height of this is hi, the height of the tree image. So what we can see here is the base of this triangle is do, the height is ho. The base of this smaller triangle is di, and the height is hi. So I see that do over di is equal to ho over hi. Can we find another pair of similar triangles? Let's see. I know that this triangle right here has one vertex on the center of curvature C. Do you see another triangle that's similar to that one? This one right here. These two triangles are similar. How do we know that? Well, right here we've got vertical angles. They make a shape like a bow tie. And I know that vertical angles are always equal in measure to each other. So we have two right triangles again that share an angle here because they're vertical angles. In the first case, it was because the angle of incidence equals the angle of reflection. We can set up another relationship with these two. I compared ho over hi for the first two triangles, the yellow ones. Let's do the same thing for these pink triangles. Here I see that ho over hi must have the same ratio as this distance here. What is this distance from O to C? Well, I see that it's a distance that's less than do. How much less is it? From here to here is do minus some amount. The amount that we're minusing, subtracting, is this distance r. So this bracketed distance here is do minus r. What about this distance up here? This distance I see is less than r. How much less? It's di less than r. So we call it r minus di. So ho over hi must be equal to dou minus r over r minus di. So now we have two equations that are both relating to ho over hi. I know if dou over di equals ho over hi, and this expression on the right equals ho over hi, if two things are equal to the same thing, they must be equal to each other. So we can eliminate all our h's here and get something a little bit simpler. That tells me that dou over di is equal to do minus r over r minus di. Now, right now, to investigate this relationship a little bit further, I would like to cross-multiply, and see how can I simplify this in a way that doesn't involve any fractions for the moment. So let's do that. So we've set the means equal to the extremes with these fractions, and now we need to distribute. Now we want to distribute do onto this binomial on the left and distribute di onto the binomial on the right. So we've got... Now I notice in this equation that there are four terms, and each of them has two of our symbols out of the three. We have three symbols, di, do, and r, but in each of those three, one of the three factors is missing. So if I took this whole equation and divided by the triple product, di times do times r, then let's see what happens here. I'm going to cancel the do and r if I divide by these three factors, and I'm going to end up with 1 over the factor that is missing from that term. So my equation is going to look like, here I'm missing a di, I have 1 over di. Here I'm missing an r, so minus 1 over r. Again here we're missing the r, so minus 1 over r. Here we're missing do, so I have minus 1 over do. Now you might say, first we got rid of fractions and now we brought them back. Why would we want to do something like that? Well, we're looking for a certain kind of symmetry in this expression that'll help us to make meaning. So let's see how much further we can simplify it. I see that I have some like terms here, a 1 over r and a 1 over r, so I could collect my 1 over r's on the right, adding 1 over r to both sides. I'm going to have 2 over r here, and then I can bring this 1 over do to the other side by adding 1 over do. So I see that I have 1 over do plus 1 over di equals 2 over r. I like the symmetry of this expression here, but it would be nice if we had something a little bit simpler here. I have a 1 over and a 1 over and then a 2 over. How could we simplify that further? Well, I know that I can flip any fraction if I make the following adjustment. I have 1 over 1 over do, let's be consistent, plus 1 over di is equal to 1 over r over 2. So the 1 over r over 2 is the same as 2 over r. R over 2, notice, is halfway between C and the mirror, and for reasons that we will see, that location is called the focal point of the mirror. Here it happens to look like the location of that image, but it just happens to be close. So what we're going to define f is equal to, I use a triple equals for definition of a new symbol. F is equal to r over 2, half of the radius of the mirror. And making that adjustment, since I have an r over 2 here, I end up with my mirror equation. 1 over do plus 1 over di is equal to 1 over the focal length of the mirror. And in a future video, we can look at the symmetries of that mirror equation. 1 over do plus 1 over di equals 1 over the focal length. I see that these add really nicely when I take not the numbers themselves, but their reciprocals.